Today we're going to look at John Conway's Game of Life with a Python implementation using nested loops. It's designed using the pygame-zero game engine and made to fit real well with the Mu editor, a great tool for getting started with Python. I'm Paul Lawson and this is Computer Science Foundations. Let's go ahead and just glance in at the code right off the get-go here. Scroll back up to the top and get over to here. We got a small little code. We got our setup on here, rows, columns, cell size. And these are the parameters. They're going to be constants throughout the code. It's a Python coding convention to use all caps and underscores to separate the words for constants. Now, the language itself doesn't prevent you writing code that reassigns to that. That would just be against the coding conventions. And the purpose of coding conventions is to basically let the author give the intent of the code. Sometimes there's tools outside called lint that might analyze the source and see if the source matches the coding convention's intent. But that's a different story altogether. Now, before we get too far, let's go ahead and just run this program and see what's going on here. This is John Conway's Game of Life. It was first published in October 1970 in Scientific American under an article about mathematical games by Mr. Gardner. I remember that first name. And since then, it's become hugely popular especially amongst people studying with computers. It didn't require a computer to run. It was, people could do it on graph paper, doing one scene after another, kind of like a little flip book animation. But it got more interesting if you did have a computer. However, in 1970, not many people did. So purportedly, there were millions of dollars in computation spent with people doing this on the side on their computers at work. So as this game is running, you can see certain things are showing up here. There's a bunch of interesting activity, hard to describe what's going on there, but there's definitely a lot of little things that have just kind of like little islands have stopped. These are called still lifes. They're not doing anything. And then there's other ones here. You'll see right there, little things that are like blinking. And every once in a while, you'll see perhaps a glider move around somewhere. This thing has a few events built in. I can stop everything. I can clear the screen. I can generate random numbers. I should get rid of the red notions. I could step. So if I'm stepping through, you can see how the generations proceed. So it's a small little example. Gives you a few events and certainly encourage you to begin to explore the code yourself. Oh, right there. I'm looking at that. I'm wondering what will happen with that one. Looks so nice and symmetric. All right. Well, let's get back to the code we're looking at here. So let's read not many documents in the front here, but Conway's Game of Life. He uses pygame-zero framework and see the key event handler at the end for commands. All right, let's go look at the end of the file because that's where everything seems to start up. Let's see, we got the very end. We're calling this function called build grid. We're making a world and a world next. And here we're using those constants, rows and columns. Let's look on the same side. And this must be where it's random. Now I wrote this code here. Adapted it quite a bit from some original stuff here. But so I do know what's doing. But let's go look here. Now the next part up here is the key down. Okay, here's on key down. And yeah, sure enough, we're seeing something for the space bar. There's the space bar. There's the C key. There's the R for the random and the step. And it does look like they're using these global variables here. Only a few global variables. Yep. Now there's a key down. Oh, I see there's also a mouse down function here. And if we go up here, I guess I can select. Just looking through here, there's an update. There's count neighbors. There's draw, cell draw, random, the grid random, grid clear, build grid. That's it. So, if you've written the code when we did stuff with Turtle Graphics, I remember where we had to register for key events and we had to register for a mouse event. I'm not seeing any of that in here. So where did that code go? Why does it seem so simple and so short? Well, the short of it is it's written in built using a game engine, and it's the pygame-zero. So let me go and click over to here. So there's a real simple overview of what it means to write something that works with a game engine or some sort of framework like that. And the basics is that part of the code is already written for you. The main, is all done as part of a code, and all we do is supply the game-specific logic. Now here's one when I first looked at the code, I was going, what's this width and height? How is the window being set up? I was looking for a function call. Well, there's not one, because our code is supposed to declare some constants for height and width, and then when the program runs, they just use those symbols. So it avoids me having to make a call. I certainly can't change it. It has to be set up once and for the rest of the game. The second part is, where are all those event registers happening? Let's just clear that up. And we don't have to, because when our code is loaded up, the game engine will actually look at our code looking for entry points. In this case, it finds one for update, for draw, and 2 event handlers for the key and the mouse down. So if it's a loop or it's an on-timer event, I really don't know how it's working, but this is kind of pseudocode for what's happening. So the game engine is going to call update, give our game a chance to update the state of the system, and then it's going to call draw. And from reading the pygame-zero documentation, it says it's going to do this about 60 times a second. Now, if our code took too long, it wouldn't be able to do that, but it's not going to call faster. So if our code's simpler and we're on a fast machine, that just means the rest of the time is given back to the kernel, and the machine can actually rest. So that's another part. The game engine is taking care of the timing for us. So in a nutshell, this is what it means to work with a game engine, and this is what makes the code a little bit shorter. Now let's go back and take a quick gander at what this game of life is about, because we saw some of those patterns. Let's clear that out. And you know, some of it's going to be your own homework. You can go look at it here, and we'll look at it in the source. But here's an example of one of those patterns we saw. It just stayed there. And in cellular automata, they call this a still life because it doesn't change. And I put these numbers here, like 2, indicates that this cell is adjacent to 2 other live cells. And the same goes, of course, for this one, because it's adjacent to 2 live cells. And I guess I could complete this all out. See, all of them are adjacent to 2. So it fits there. So the basic rule says, hey, if you're next to 2 or 3, you're happy, you're comfortable, you're going to be just fine the next generation. And so that's why in generation n plus 1, those are all going to be there. Now the second rule that kind of comes into play is what cells will come to life. And the rule is, if it's exactly 3, then that'll actually come to life in the next generation. So in this case here, the center one is next to 4, so it's too crowded. It's not happy there. And all of these on the side are they're not going to work either because they're next to 2, not 3. So generation n plus 1, and for that matter n plus 2, n plus 3, etc., will always be the same. So this is a stable pattern. Now another one you'll see real commonly is an oscillator. That's a pattern that repeats, and the shortest repetition can basically be, you know, every other generation. Some take more generations than that. This is one of the simplest, and it's called the blinker. So the one in the middle is adjacent to 2 live cells, so he's going to be there in the next generation. He's all happy. The ones on the end, however, they're kind of lonely. They're only next to 1. And so he's going to die in the next generation. However, the ones over here are adjacent to 3. This is an example of what it means to be next to 3. So this empty cell is next to 3, and so he's going to come to life in the next generation. Now I didn't go through every other one, but you can kind of see that this cell over here and the one over here and over here is not next to 3. So, and that's it in a nutshell. Now these 2 patterns are easy to guess and understand what's going on. You could look at these and I'd say, hey, look at those and can you figure out why they're just stable and they're going to stay there? Now, what if we added 1 dot? What if we added this 1 dot? What would that take? If you had a piece of graph paper, you could draw it out and you could figure out, oh, well, let's see. This stuff's all the same. But this cell, look at this cell right here. This cell is next to 1, 2, 3. So he's going to come to life. Same goes for here. It's all symmetric, so we can see that. Now we could work this out on graph paper, but you'd get tired. So let's just take a glance at the code and see how it's actually going about its work. Let me go ahead and stop the one that's running in the background. Oh, let's get rid of that red mark. Okay, so we had that key down. These are all things just to clear out the screen and do some stuff, but where's the core of this work done? Update. So again, this is where the game engine calls us and say, hey, figure out the next generation. And so there's some code here that's allowing us to work with those keyboard events. So we have this idea of running and not running. So if the game engine calls us, but we're not running, will just return. So no update to the field. If so that's that case right there. If we're in step mode, we have to be running to actually take a step. But if we were in step mode, then after running, then it's going to actually set the running to false. So it clears that. It clears the running if step is true. And then there's this bit about being changed. So if you actually make it down to here, down to this line from here on down, we're committing to actually changing the generation, either because of step or because we're free running it. So let's look at what's happening inside of here. For R in range rows and for C in range columns, we're going to basically visit all the rows and columns, and we're going to say, oh, here's the core. Here's the crux of the algorithm. So the next generation at row and column is going to be equal to, scroll down. There we go. So if it's currently alive, so a live cell stays alive if it's not lonely or crowded. So here, world next. If n is greater than or equal to 2 and less than or equal to 3, you could say 2 equals 2 or 3, but this is the way the rule's written, so we'll just be consistent with it. It'll stay alive, so it's going to be equal to true. And because the way this is written, this is a Boolean expression here. So if it was 0, 1, 4, 5, 6, 7, or 8, those are the total things. If it's any of those, it's the flip side, it'll be false. So we didn't have to actually add an if and an else in here. We just said it's equal to this Boolean expression, and this is a Boolean value, so it just assigns it. The next one, so if it wasn't currently alive, then its next state will be true if and only if the number of alive neighbors is 3. So in a nutshell, if we want to change it, we could just tweak that number. I think we'll do that in just a second, but right now we'll let it run. Now, when this code ran, notice that we're putting our answers in the world next, and we're reading from world. And that's because we can't modify the current world while we're calculating the next world. Otherwise, the next values would begin to affect the current ones. So we can't do it in place. We actually have to do it in that second grid. Now, once this is all done, notice here there's a code right there where we're now reassigning over next world back into world. So next world was used as a scratch pad to calculate generation n plus 1. Once this is all done, it copies it back. And that was all that happened in update. So we're not doing any drawing in this code. That's because the game engine is going to turn around and call the function draw. And in the function draw, this actually says, hey, did anything change? Now, if we were suspended and the game engine continues to call update over and over again, but the way the logic was down there, if it's suspended, we won't actually be changing the changed flag. So that means when it's idle, we won't have to constantly redraw the picture. It's just happy doing it, leaving it as is. But when it is there, we'll go ahead and fill the screen, and then we'll do for row and column, and if it's true, we'll go ahead and draw the cell. Now it's done this way here. That means we fill the background once for all the cells, and then we only have to paint the ones that are actually alive. And since in any typical game, basically there's probably like less than 5% of the cells that are alive. That means we don't have to draw all of the background ones. We just paint the background once and then put little polka dots where they exist. All right, so that's the draw event, and then draw just turns around and calls cell, and then this is pygame-zero. Notice we didn't have to include screen or create a new instance of it. It was just provided by the environment we were at, so those variables were already defined when our code was included. So screen.draw.fillDirect will take care of it. So that's a little simpler than we had to do when we were working with the turtle graphics. We love turtle graphics too. It's a great way to start. And then here are the functions for clearing it and just generating the random. And here's looks like here this determines approximately when we make it random what ratio. So it's 1 in 7 chance that it will be live when we first start. So I'm looking at that code here. Let's go ahead and run this code. All right, here's our game going. And sure enough, I can hit spacebar, I can clear it, I can make it random, I can step. Notice all those ones that were individual ones, they were lonely on the first generation. So if you clear it out, do random, you can see that things like, okay, here there's a bunch adjacent. That's going to be okay. But these single cell ones, they're going to die away. Now let's go answer that question we started early on here. Was if I go ahead and make that, if I get that little dot, remember this was, so I can run this one. It's not doing anything. I'll stop it. Add one dot to it. Now let's see what happens when we run this guy. It blossomed and then it got idle again. So let's do one more dot and see what happens. Now the thing that blossomed kind of exploded into the other side. And it just keeps going. Now, if you were doing this on graph paper, this would get pretty tedious to calculate all of that out. And there I just saw two gliders show up that crashed into each other. Here's a glider right there. These guys, this guy. And they'd go on. In this case, they're hitting the edge of the field, so they're stopping. But otherwise, if the universe was infinitely large, they just continue on until they ran into something. And this is a little fun game on here, is that notice that there you go. These guys just ended up colliding and then becoming idle. So now this system is basically stable. If it wasn't for the ones that were going off into infinity, they'd continue on, but this one's come to kind of a standstill. All right. Well, we have gone through a handful of pieces. Let's just capture on here. We covered a game engine. We talked about globals being all caps. Globals with G underscore prefix. Our constants are all caps. We have event handlers. We're using nested loops. The main loop is something that's taken care of for us by the game engine. We don't have to take care of that. The game of life, cellular automaton, that actually was something that was kind of developed by Alan Turing and John von Neumann. They both did independent work, and that's what stuff John Horton Conway has based his game of life on. We saw the still life as an example, oscillator, the glider, those moving. A zero-player game, that's what this is in a sense. Once you start it, it does something that's of curiosity, and it does stuff that's unpredictable. So that's an element of it. Well, that's John Conway's game of life using nested loops and CS foundations. And if y'all go ahead and like and subscribe if you want to see more. Thanks. Take care.